So again, if you're having a hard time with section 2.3, please ask questions. This is one of the tougher sections that we deal with. It's pretty complicated technically. It seems like there's different ways of doing things. And there's really two ways to do these types of problems. We talked about method 1 and method 2. Method 1's pretty good if you're dealing with lines. If you're dealing with almost any other kind of function, you want to go with method 2. But I'm going to do some practice here. Let's say we have this. And let's say we want to show let's see here. We're going to go with a given epsilon, say 0.1. So let's say we're going to try to show this. So I'm going to go with method 2. And what method 2 is, I'm going to solve for x. I'm going to start with the setup for the limit. So we're going to get something like this. Now, filling in what we know, f of x, square root of x plus 1, minus 1, and we're going to go from epsilon of 0.1. Now, we want to break this up. And again, this is a principle from algebra. It might have been a while since you've seen this. And again, this is what makes calculus good. It also makes it kind of difficult, is it's a big review on algebra. So again, it's this idea that the absolute value of u less than c, you can rewrite this like so. So again, this is this little factoid from algebra kind of review. So we're going to do the same thing with this. There we go. And this middle part here is going to play the role of our u. So what we could do, let's see here, we can add 1 to both sides. Or really all 3 sides. Oh. So to solve for x, we're going to add 1 everywhere. Here, here, and here. Okay. And then now we're going to square everything. So we're going to get this. Now we're still trying to solve for x. So we're going to subtract 1 from everywhere. Let's see. So we finally solved for x. We got x between negative 0.19 and between 0.21. So with that, let's go back to this. So we have C. C in this case is going to be 0. So again, we break it up. And then x minus 0 is just x. So what we can do is we can compare this to this. Now, when doing that, we want to keep in mind that C is equal to 0. Now, negative 0.19 is over here, a little farther over 0.21. Now, we want to find a delta that is, well, it's going to work. And we have a choice of 2. We have a smaller distance, d1, and a larger distance, d2. Now, I want to think in terms of distance. So the distance for d1 is 0.19. The distance for d2 is 0.21. So what we will do is just choose the smaller distance. So in this case, let delta be d1 or 0.19. So what this says, if we're 0.19 on either side of 0, then we're going to get a difference between our function f of x and the limit of 1 that's going to be less than epsilon, which was 0.1. And so now we've proven what we were trying to show. We've proven that the limit is going to work. If we choose any value of x that's within 0.19 of 0, then our function f of x will be 0.1, a distance of 0.1 from the limit of y equals 1, or f of x equals 1. Questions about that? All right. So I'm going to move on to section 2.4. And with this, we're talking about one-sided limits. And the idea here is going to be this. So let's say we have something like this. And this is our function f of x. Now, let's take a look at the limit at x equals 4. And let's say we approach from the what we call the left side of 4. So if we think about x values on the left of 4 over here, well, as we approach, get close to 4, the function value is about 3. So this means the limit of f of x for this scenario is going to be 3. Now let's say we only look at the x values to the right of 4. Well, in this case, the limit of f of x is going to be 5. If we're only using x values from here, we're going to be over here near 5. So when we take one-sided limits, well, sometimes they don't equal each other. And that's going to happen when we have this kind of a gap or a jump. So we have a special notation for this. The way we would write this is the limit as x approaches. And instead of saying left, we're going to say minus. And instead of saying left and right, we're going to orient ourselves with the negative side of the x-axis and the positive side of the x-axis. So as we approach x equals 4, from the side of 4, where if you keep going, you'll eventually hit negative numbers, well, we're going to represent that with 4 with a minus. And so this gave us 3. So to express the limit on the right of 4, and if you look at what's on the right side of 4, if you keep going farther and farther to the right, you're going to be in positive numbers. If you're not in positive numbers already, now for 4, you already are there. So what we say is that x approaches 4 from positive infinity or positive infinite numbers, infinities that contain positive numbers. F of x is equal to 5. So what we're doing is we're letting minus be the left side of the number and plus be the right side of the number. So any questions about that? So let me do an example with this. Oh, one thing, I do want to mention one last thing. So let's say we have this. Seven. Now, let's take a look at this limit. Label that from x here. So as x approaches 4 from the left, we're going to be very close to, well, a function value of 7. Likewise, if we approach 4 from the right, again, we're going to have a function value of about 7. So what we've done in the past, though, is we've dealt with this plane limit where we don't have minuses and pluses on our numbers. And if we go back to this idea that, well, regardless of left or right, if x is near 4, f of x is near 7. So this is what we've got so far. This is what we've been working with. And this actually comes together what we call the limit existence theorem. And what it's going to say is this. This sort of plane limit only exists if these two exist and they're equal. So in other words, the limit as x goes to c of f of x equals L if and only if the limit as x approaches c from the left equals the limit as x approaches c from the right, it's equal to L. So any questions about that? All right. So let me run through an example on this and just kind of show you how this works. So the plane limit, the limit that's just what we've been working with so far, it only exists if the limits on the sides of that point, they exist and they're also equal. So let's say we have this. So let's say we have this. Well, this is our f of x, and it's an unusual f of x, I'll admit, kind of a neat f of x. But this is it. So let's start with -1 here. What's the limit of f of x as we approach -1? Well, first off, as we approach -1 from the left, we can't. F of x isn't defined here. So this limit does not exist. There's no way we can pick any values to the left of -1. Now, we can say that the limit as x approaches -1 from the right, this does exist. And so when we're near -1 to the right of it, our f of x value is about 1. So here comes the big question. Does the limit as x approaches -1 of f of x, what is this? Again, it's going to kind of depend on what someone's asking you. If they're assuming that we're only using x values in our domain, they might be writing this when they really mean that. So you want to be careful of that. But based on what we've looked at, there's no limit on the left side. So this limit exists, but this one, you want to make sure people know that at -1, the function stops. So this doesn't exist. We do have the right-sided limit, but that's it. Now let's take a look at 0. Little dot there for 0. Now, if we approach 0 from the left, well, our function's decreasing until it hits that x-axis. So the function value is 0. Now the limit is x approaches 0 from the right. Well, same thing as you use x values on the right, f of x is dropping down to 0. So that's also 0. And because these two are equal, and we can also see it on the graph, we can do that. So in general, this limit exists. Now let's take a look at 1. As we approach 1 from the left, we're climbing up, 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 and we get to an x value or f of x value of about 2. This is going to be 2. But if we approach 1 from the right, well, approaching from the right, well, you're going to have a value of 1 for your f of x. So we've got 2 different values for the 2 different one-sided limits. So that's going to say that the limit as x goes to 1 of f of x does not exist. Questions about that? All right. Now let's take a look at x is 2. Well, as you get close to 2 on the left, your f of x, it's 1. So that's 1. And then the limit as x approaches 2 from the right, over here, well, you're still at an f of x value of 1. Now again, this whole here is not going to be a problem when we're dealing with limits. Because we're talking about limits, we're talking about x values very close to 2, but not actually at 2. So this we can actually ignore. And what we're going to get is the limit as x goes to 2 of f of x is equal to 1. Questions about that? All right, there's one more. So for x of 3. Now in this case, if we approach from the left of 3, we're at f of x value of, again, about 1. But then if we try to approach 3 from the right, we're going to run into a problem. We don't have a domain for this function to the right of 3. So we can't do this. We can't use any x values to the right. So this doesn't exist. So when we talk about the limit as x goes to 3 of f of x, again, you want to be careful. You want to make sure that if someone talks about this, they're thinking both of these. Sometimes someone might think, well, as x approaches 3, only using values of x in the domain of the function, which is just a fancy way of saying they really mean this. But we're going to go with how we've been studying these one-sided limits so far today. We can't choose x values on the right. We could on the left. So this is not going to exist. And again, we're treating this as you're free to choose x values to the right of 3 and to the left of 3. And because our domain doesn't exist to the right of 3, we can't do that. So that's what we've got for one-sided limits and the limit existence theorem. Now, one-sided limits, especially stuff like this and this, those are going to be important. So it's not just an academic exercise. And certainly in Calc 3, you'll run into some things where you want to make sure that the end of one interval and then the end of another interval, when we're describing properties of f of x, we'll use one-sided limits to make sure that we have continuity on one side and continuity on another side of an interval. It depends what we're doing with f of x, but sometimes that is required. All right. So as there was a precise definition for the limit, we have a precise definition for one-sided limits. Now in the homework, they don't really have you doing much with this, at least the homework as it's shown in the text. So that, hopefully that gives you a little bit of ease so you can focus on the proofs for the third section. Let me go through what these definitions are. So first off, we have the right side. With a plus. So the limit as x approaches some number on the right of f of x is L if for every epsilon greater than 0, no matter how small you want to make epsilon, there exists a delta greater than 0 such that for all x that are going to follow this condition. So here's c, here's x plus delta. So you have c plus delta. So this is a number bigger than c. It's to the right of c. X is between these two numbers. Then difference of f of x to L is less than epsilon. Questions about that? So if you have something like if you pick x between c and c plus delta, well, then you're going to have a value of f of x between L and L plus epsilon. And that's what that's going to be. Questions about that? So for the left side, so this is the minus. So approaching from the left, the limit of this function is L if for every epsilon greater than 0, there exists delta greater than 0 such that for all x between c minus delta and c, our function is within epsilon units of L. Questions about that? So I'll give you a particular picture just to kind of illustrate the concept. So if you choose an x between c and c minus delta, you're going to get a function value between L and L minus epsilon, or at least in this case, it'd be L minus epsilon. So any questions about that? So that's the idea of the exact or the more precise definitions for these. Let me run through an example how you do this. And again, looking at the homework, they don't seem to be emphasizing this as much. But let's say we want to prove that the limit as x goes to 0 plus the square root of x is equal to 0. So RC is 0. And L is equal to 0. So we'll take our f of x minus L less than epsilon, or square root of x minus 0 less than epsilon, or square root of x is less than epsilon. Now, in the past, what we would do, and we'll still do this here, again, we can break this up. Negative epsilon, square root of x, positive epsilon. Now, we're going to make a little note here. Since x is approaching 0 from the right, x is always positive. So this means the square root of x is greater than, or let's say greater than 0. We're to the right of 0. So we're not going to ever equal 0. So square root of x is always greater than 0. It's always to the right of 0. It's not equal to 0. A little more 0-like. So that means square root of x is going to be, of course, greater than 0. So instead of having minus epsilon inequality, square root x inequality epsilon, you know that this is going to be the case. So now we're going to square everything. So we're going to get this. So we're going to hang on to that. We're going to now take our x and our delta expression, and we're going to solve for x. Now, for this, though, it's fairly, well, it's done pretty much for us. The way this definition is set up, well, there's x. Well, all right, I guess we don't have to do much solving. Now, we know that c is 0. This is the number we're approaching from the right. So we have 0 less than x less than c plus delta. Oh, sorry, 0 plus delta, or delta. So what we can do here is, as we compare these two, what we get is that delta is going to be epsilon squared. And so that's where we finally found what we're looking for. And so now we can give our complete answer. And that's going to be it. So any questions about that? Again, looking at the homework, they're not really emphasizing that, but just to go through it, just so you can see it. All right. So the last thing in this section is it involves the limits of sine theta over theta. And a lot of these types of problems, they're really interesting exercises in algebra and your limit properties. Now let me check something. There's a property, I want to make sure that we mention this in section 2.2. Let's see if this came up. Yes, we did cover this. I'm going to bring this one back. This is a key one. But the limit as x approaches c of a constant k times f of x is going to be k times the limit as x goes to c of f of x. Now, this is a very common thing we're going to have in this class. When we deal with derivatives and we deal with integrals, the constants are going to pass through the derivatives and they pass through the integrals, just like it's passing through the limit. So let's take a look at this function. So we bring this property back. We're going to use this. The f of theta, sine theta over theta. Now, there's an analytical proof to this. I'm just going to give you sort of a graphical proof, or just sort of an illustration, really. And as we take a look at this, what this looks like. There's a hole here. And the reason being is that we've got 0. Theta is 0. This is our theta axis. Well, we get a division by 0. So we're going to get a hole. Now, that doesn't mean the limit doesn't exist, of course. And if you think of it in terms of a left side limit and a right side limit, they're both converging to 1. So what we get is this. The limit as x, or in this case theta, approaches 0 of sine theta over theta is equal to 1. So what are we going to do with this? Well, we're going to get into some fancy problem solving. And this one kind of, it gets some algebraic gymnastics, and it can be kind of fun. So I want to show you some tricks that are going to help, and they're tricks that they might not totally be obvious, but actually they may not be obvious at all. So let's take a look at some of those. And again, this is what calculus is really great for. You can learn some neat algebra along with your calculus. Now what we can do is we can break this up. We can do this. And because we're taking limits, it's okay for us to simplify. And there we go. So now we can distribute this. So these first two limits aren't too bad. Here it's really a polynomial, and we have that polynomial rule that says we can place the x with the 0, just like it's an algebraic substitution. So this will be 0 over 2 is 0. And then the limit of a constant is just that constant. So we get 0 minus 1/2 plus, now this one, I'll do a little work with this one. What we can do, this 2x down here, we can treat this as the limit as x goes to 0 of 1/2 times sine of x over x. Because 1 times sine is sine and 2 times x is 2x. So we'll get negative 1/2 plus 1/2 limit x goes to 0 of sine x over x. All right, so the constant passes through. This is equal to 1. That's what that little theorem does. So we know from studying that graph, and there's again an analytical way of showing how to do the proof. They do have it in the text. This is going to be equal to 1. So what we'll get, negative 1/2 plus 1/2 times 1, and that's just going to be 0. So that's one example using the sine x over x. It can get a little more interesting. So let's bust out some algebraic amusement. All right. Let's say you have this. Now this is a whole heap of trouble. If we just substitute 0 for y, sort of like using our polynomial rule. And we can actually do that with trig functions too. We're going to have a problem. Now, sine of 3 times 0 is the sine of 0, and well, that's just 0. Great. But if you take the cotangent as y goes to 0, well, that's not going to be a problem. I mean, you're going to get the cotangent of 0 when, oh, wait, ooh, that is going to be a problem. Cotangent's undefined at 0. There's actually a vertical asymptote. So, not going to work. Same thing you're going to get here, and then you're going to have a times 0. So you're going to get a 0 and undefined. Well, actually, it's going to turn out to be infinity. But we'll talk about that later. Same thing here, and then you have a 0. So this is really quite a mess. You have a 0 in infinity. In infinity, we'll talk about how you get limits that result in infinity later. In a 0. What's infinity times 0? Because remember, infinity, maybe no one's told you this before, it's not a number. It's really a concept. Like numbers times 0, 0, we're done. But infinity is a concept. One way I like to think of infinity is it means keep on going. So what if you take that and multiply it to 0? And we can have a philosophical discussion about this, but for now, we're not going to mess with that. So what do we do here? Well, we're going to get creative. We're going to use tools that we've learned about that will hopefully give us an answer. So first off, let's break up these cotangents. So let's take sine 3y, and this will be cosine of 5y, sine of 5y, over y times cosine of 4y over the sine of 4y. Now let me share with you the method of my madness here so you see where I'm going with this, because this is just going to seem like random stuff. I'm going to try to come up with as many sine thetas over theta that I possibly can. Now cosine, we can replace the y and the cosines the same with 0, just like we do with polynomials. And cosine of 0 is perfectly fine. It's equal to 1. So the cosines, we're not going to worry about too much. But these sines, we're going to try to get them into a form that's like sine theta over theta. And this is where the creative algebra comes in. So if you haven't seen this before, this is fine. This is going to be a new thing. Hopefully it's going to be a cool thing. So let's simplify this down here. Sine of 3y times, now what will happen here, this sign is going to jump down. So I have cosine of 5y, y times cosine 4y, sine of 4y, times sine of 5y. So I'm going to simplifying this from being a compound fraction to just a regular fraction, or put another way, a compound rational function to just a regular rational function. And you can multiply top and bottom by sine of 4y. And so we've got this. Now, if you're not sure what I did, you can multiply again top and bottom of this by sine of 4y. So sine of 4y are going to cancel. And then you'll just have sine of 4y on top here. Any questions about that? Right. So what can we do with this? we still have some issues. If y is going to go to 0, and we use our polynomial method, where we would just replace the y's with 0, 0, 1, 0. Cosine of 0 is 1. 0 times 1 times 0, we got division by 0. Still not out of the woods. So this is where we're going to get kind of clever. I'm going to rewrite this again, make it smaller. Same approach is going to make it fit a little better. Let's see here. So I'm going to break things up like this. Now, the problematic terms here are my sines. My cosines, again, if I let y be 0, cosine of 0 is 1, cosine of 0 is 1, 5 times 0 is 0, 4 times 0 is 0. So 1 over 1 is just 1. That's not a problem. But here I've got a division by 0, and here I've got a division by 0. So what we're going to do is this. I'm going to put a 3 here and a 3 here. Multiply top and bottom by 3. Let me see. You're right. You're absolutely right. Sorry about that. It's cosine 5y on top, cosine 4y on bottom. Thank you. Yeah, I'll just keep going down the rabbit hole. Thank you for letting me know. So we're going to do top and bottom by 3. We're going to keep our cosines because they're not going to be an issue. Now we're going to do something kind of tricky here. I'm going to highlight these as blue because these are important. Make them stand out. I'm going to put a 4y and a 4y here. And what I'm going to do with this one, I'll multiply top and bottom by 5. And there's a reason why I'm only doing 5. You might be able to see what I'm getting at here. If I let theta be 3y, then I have sine of theta over theta for this one. If I let theta be 4y, I'll have sine of theta over theta for this one. Now the tricky part is I've got this extra y here. So what I'm going to do is I'm going to shift this over to here. And I'll have a y and a sine of 5y. But I want 5y. So anticipating that I'm going to shift this y over to here, I'm going to multiply top and bottom by 5. So there's a 5 up here waiting for that y. So this is what we're going to get. 3 sine 3y over 3y. Cosine 5y cosine 4y. And then this one will be 4 times sine of 4y over 4y. And this y is going to be moved over to here to get 5y over 5 times the sine of 5y. Now there's a couple tricks we got to do. A couple more. So this will become 3 sine of 3y over 3y cosine 5y cosine 4y times 4 sine of 4y times 1 over 5y sine of 5y. Questions about this? So the last thing to do here, and again, this is an algebra thing. So if you have 1 over b over a, this is a over b. Or put another way, a over b can be written as 1 over b over a. Now, the way this works in real life is that you can say 1 over 4/3 multiply top and bottom by the reciprocal. And then these will cancel. So you can do something like that. So what is this going to do? Well, particularly interested in this one. We can rewrite 5y over sine 5y as 1 over sine 5y over 5y. So in other words, 5y sine of 5y is 1 over sine of 5y, 5y. We can do that. And so what that's going to mean is that this, take the limit, as y goes to 0, of 3 sine 3y over 3y cosine 5y cosine 4y times 4, a little more room here, sine 4y over 4y, and then 1/5 we'll get something like that. So it's quite a journey, I'll admit, But once you get the hang of it, it can be kind of fun. Now in this case here, our theta is 3y. The theta is 4y. And here the theta will be 5y. And the key thing to see is this. As y goes to 0, then 3y, 4y, 5y go to 0, or theta goes to 0. In either case, theta will go to 0. So y going to 0 is the same as 3y going to 0. It's the same as 4y going to 0. It's the same as 5y going to 0. Questions about that? So what does this become? Well, we'll get 3 times the limit as y goes to 0 of sine of 3y over 3y times the limit as y goes to 0 cosine 5y cosine 4y. And again with this one, we're going to use that polynomial property where we just swap out the y's for 0, we're going to be fine. Times 4 times the limit as y goes to 0 of sine of 4y over 4y times 1/5, and this is going to be the limit of y goes to 0 of 1 over sine of 5y over 5y. Whew. Again, we're using that property that the limit of a product is the product of the limits. And we're letting the constants pass through the limits. So what we're going to get is 3 times 1 times, now this will be cosine of 0 over cosine of 0. Again, we're going to use that substitution rule we use for polynomials. Times 4 times 1 times 1/5 times, and now we've got the limit of a quotient is the quotient of limits. I'm going to erase this so it's a little easier to see. So what we're going to get, 3 times 1 times 1 over 1 times 4 times 1 times 1/5 times, well, it's a constant, so that's just 1. And this is going to be 1. So 3 times 1 times 1 times 4 times 1 times 1/5 times 1, this will come out to 12/5. Whew. And that's going to be your answer. Questions about that? So these types of problems, you can get some algebraic gymnastics, and they're kind of fun. You got to kind of stick with them. And if you have any questions, let me know. All right. So that's section 2.4. We're going to get into section 2.5. And the thing with 2.5, we're talking about continuity. Now, continuity is basically a continuous function in a nutshell. Is a function that doesn't have any gaps, not necessarily smooth. It doesn't have to be smooth, but it doesn't have gaps or holes. It doesn't launch off to infinity or negative infinity. And it doesn't have infinite oscillations. So a continuous function basically looks like this. A good example are polynomials. So you can have a polynomial doing something like this, as polynomials do, but you could do something where it keeps going and then it makes a corner. That's perfectly fine. And then maybe it kind of does something like this. It goes just constant for a while. You could do something like that. But the key thing here, these are the things that are missing in this picture. There are no removable points. So what a removable point is, it's basically a hole. So you have a removable point at x equals c. So this doesn't have any of those things. There's no holes in it. Now this little corner here, that's perfectly fine. Where corners become an issue, we run into problems with derivatives on corners. We're going to run into some things there. And but for continuity, they're okay, totally fine. So no removable points or no holes. Let's see. There are no jumps. So this would be a jump at x equals c. You just suddenly leap in value, or you have a value at c and then you suddenly start over again at a higher value beyond c. There's no smooth connection between this location and that location. So there are no jumps. Now, functions can go off to infinity and be continuous. That's fine. But what we're looking for is, and that's as these go on and on forever. But we're looking for a function, we want to be careful of functions that reach for infinity at a particular point c. So an example of what this would be, vertical asymptotes. So the idea is a function is not reaching for infinity at some particular point. This would be a discontinuity at point C. Now, as a function goes on, it can eventually just rise up to infinity or dive down to infinity as we go to infinity. That's fine. But at every point x value along the x-axis, if we plug in that x value into the function, we're going to get a finite number. Those finite numbers just might be getting bigger and bigger, but that's okay. Here, though, if we plug in c, we're going to get something that's undefined. And that's where we run into problems. So when you have a vertical asymptote, that's going to cause the function to launch off to infinity at a particular point. Finally, I'm going to attach this adjective infinite oscillations. It's not just oscillations. Like sine function oscillates, that's fine. There's no jumps, there's no gaps. It's a, as you'll discover later on, it's a reasonable function. An infinite oscillation, something like this. It oscillates so much around C, you can't actually figure out which f value this function's approaching as you get close to C. A good example, sine of 1 over x near C equals 0. Kind of a classic example of that. Something to be careful of. So no infinite oscillations. There's no particular point that's sending the function to infinity. There are no jumps or gaps, and there are no so-called removable points or points that have been removed, like a hole. Those are all discontinuities. And when we don't have those, we're going to get something that's going to be continuous. Now, just like with limits, continuity can exist at a point depending on which way we approach it. Now, generally, f of x is continuous at x equals c if the limit as x goes to c of f of x equals f of c. So in other words, f of c has to exist. Again, that's the problem with vertical asymptotes. And then the x values near c, well, they're going to give you f of x values that are close to f of c. In other words, no gaps or anything like that. This is also a reason why the hole doesn't work. If you have a hole at c, then f of c doesn't exist. So the limit will exist, but f of c won't exist. So we have right continuous, and we'll do an example kind of going over these. So for this one, well, here, the limit, as you approach c from the right, f of x equals f of c. So something like this This would be right continuous. So here, the limit as x approaches c plus of f of x is the same as f of c. So as long as we're on this side of c, the closer we get to c, the closer we're getting to f of c. So that works in this case. Now for left continuous, well, the left-sided limit for f of x is equal to f of c. So along this part, the limit as x approaches c from the left of f of x will be the same as f of c. So that's left continuous. So let me do an example of identifying these. Just check the top. Okay. So let's say we have this. So let's take c as -1. Now, for c as -1, we can only approach this from the right side. So the limit, if we try to approach from the left, well, that doesn't even exist. So if we don't have a left-sided limit, we can't talk about left-sided continuity. Likewise, though, we do have this. Maybe not as much likewise, but the limit of f of x as we approach from the right is equal to 1. And then f of -1 is also equal to 1. So because the right side limit equals f of x, or f of c, we have right side continuity. Questions about that? Now let's go for c as 2. If I'm going too fast, let me know. Now in this case, the left side limit is equal, it's about 0.5. And then here, put that in there, 0.5. Now the right side limit though, well, I mean, there's nothing there. We don't have any domain to work with. That doesn't exist. Now this one has a catch to it though. What's f of 2? Well, f of 2 equals 1. So we've got a problem. Even though this does exist, the limit as x goes to 2 from the left side does not equal f of 2. So in this case, at 2, we have a discontinuity. And this is kind of obvious, I guess, if you go back to just our, well, maybe it's not obvious, but if you think back to the 4 things that were discontinuities, oscillations, holes, infinities, and jumps, well, we've got a jump here. So we don't have any continuity. Now, oftentimes, usually, even though we don't have general continuity, we can usually get a left side or a right side continuity, like we have here for right side. But this one, we don't get either. So we don't get anything. So finally, so I'm just going to make a note for that last one. There's no left or right continuity. Just not there. Now for this last point, I'm going to bring in something called the continuity test. And it works like this. So we've talked about left side, we talked about right side. What about just general continuity, not just one side or another? Because that's kind of a partial continuity. What about just generally continuous? All right, so no holes, no gaps, no oscillations, no infinity. So f of x is continuous at x equals c if f of c exists the limit exists, and this is the two-sided limit. Not just from the left or from the right. So that means for this to exist, the left side limit and the right side limit both exist and they equal each other. So the left side and right side limits exist and they equal each other. Finally, step 3, this limit is equal to f of c. So this is again our definition of continuity, and we can bring all this together to come up with our continuity test. And so if we're going to say a function is continuous, not left side continuous or right side continuous, but continuous regardless of what the two sides are doing, we're going to use this test. So for c equals 1? Well, first off, f of c is equal to 2. It does exist, and it's equal to 2. Number 2, the limit as x goes to 1 of f of x, and you could get very particular about this. You could say, what's the left side, what's the right side doing? But really, if you want to sort of do it kind of faster, regardless of what side you approach 1, if you're near 1, f of x is near 2. Finally, let me replace c with 1 here. F of 1, which is 2, well, that's the same as the limit. So what this says is f of x is continuous at x equals 1. And that's going to be it. So any questions about that? So that's going to be it for today. We're going to stop there. We'll finish continuity. We don't have class on Monday, so we'll finish it on Wednesday. So we'll finish continuity on Wednesday. That's section 2.5 again. And then 2.6 here, let's see. It's just dealing with lower limits with infinity. These are actually really cool. So we'll get into what that means. And then that's it. We'll have to start talking about the first exam. So we'll finish about 2 minutes early today. If you have any questions, let me know. Otherwise, have a wonderful day. Have a wonderful weekend.